In this lesson, we are going to review the graph theory that we need to solve robotics planning problems. Here are some examples of graphs that are useful in robotics. The road network is a graph that describes which routes can be taken by a car in the city. Pose graphs are the structures used in SLAM to estimate the geometry of the environment and the location of the robot. State action graphs are graphs where the edges represent the choices we can make at each stage. Graph theory is a very rich discipline. There are many types of graphs that you can define. In this video, we are going to see the notions of undirected and directed graphs. In the next videos, we will talk about labeled graphs and multigraphs. An undirected graph is a set of nodes, also called vertices, and a set of edges. An edge is a pair of nodes, which could be the same node. In an undirected graph, there is no direction to the edges. It just means that two nodes are related. And if node A is related to B, node B is related to A. In fact, another way to see an undirected graph is that it is the representation of a symmetric relation. When we look at the visual representation of graphs, it is important to understand that we only care about the connectivity. The color and the shape that we use to draw the nodes and edges don't matter. For example, these two drawings represent the same graph. Let's count the number of undirected graphs. If we have only one node, how many directed graphs can we draw? The answer is 2. There is one graph G0 without any edge, and one graph G1 which has a loop. What if we had two nodes? In a graph with two nodes, there are 3 places where edges could go. There could be one loop for each node, and there could be an edge between A and B. There are a total of 3 binary choices, therefore there are 8 possible graphs. If you had n vertices, how many graphs would you draw? As we said, we can think of an undirected graph as representing a symmetric relation. So we can represent the graph as an n by n matrix of binary values, true or false, where each value aij tells us whether there is an edge between I and j. In this matrix, the part below and above the diagonal are symmetric, because if A relates to B, B relates to A. In formulas, aij is equal to aji. How many independent choices do we have? The number of choices is the number of elements of the top half plus the diagonal. We can find out these are n times n plus 1 over 2. This is the number of binary choices. So in total, we have 2 to the n times n plus 1 over 2 total graphs. The matrix we use to solve the counting problem is also called the adjacency matrix. In some applications where graphs have many edges, it is useful to use the adjacency matrix to compactly represent the graph in memory. But if there are few edges, this is a wasteful representation. Let's now look at the notion of directed graph. In a directed graph, there is a direction to the edges. Let's see when this is useful. Suppose you had a graph to represent the roads in a city. You could think of using nodes to represent intersections and edges to represent the roads between intersections. Suppose all the city is walkable, then we can think of this graph as representing the traversability for a person. For cars, the situation is more complex. We know that there exist one-way roads in which the car can traverse only one direction. For this, we can use directed graphs. For example, in this graph, we can see that there are two-way roads and some that are only one way. Using this graph, we can plan the route of a car respecting the rules of the road. Let's look at the formal definition of directed graph. An edge is now an ordered pair of nodes. One node is called the head, and the other is called the tail. Now we draw the edge as an arrow that goes from the tail to the head. Let's now count the directed graphs. First, intuitively, we can see that there are many more directed graphs than undirected. In fact, you can take a directed graph, forget the directions of the edges, and obtain an undirected graph. Vice versa, for each undirected graph, there are many directed graphs that could correspond to it. Let's now count more formally. How many different graphs exist with n nodes? For one node, there are 2. Either the loop exists or not. For 2 nodes, there are 4 possible choices to make. For each node, there could be a loop or not, and there could be an edge from A to B, and independently, there could be one from B to A. Can you find out how many graphs there exist for n nodes? You will find out that it's actually easier to count directed graphs than to count undirected graphs. Pause the video to think about this. Here's the solution. To count the number of directed graphs, we're going to use the idea of adjacency matrix. As before, we have an n by n matrix of true-false values. In an undirected graph, there was a symmetry constraint. If A relates to B, then B relates to A. In a directed graph, there is no such constraint. Whether A relates to B or not is independent of whether B relates to A. Then we can see that all the choices are independent, and this makes counting easier. There are n squared independent choices, therefore there are 2 to the n squared possible graphs. This table shows the number of directed and undirected graphs as the number of vertices grow. In this video, we have seen how we can define directed and undirected graphs. Once we have a direction for the edges, we will see that we can define many useful concepts that we will see in the next video.